One.
Greetings and welcome, friends. You've just stumbled upon the best part of the internet. The part where I teach you about trigonometric identities. That's right. We're starting a brand new chapter, concept, zone today. We're talking about trigonometric identities and equations. We're not there yet. Don't worry, it's going to be fine. Let's start with basic trigonometric identities. The word basic is merely there to make you feel more calm about mathematics that's going to be crammed into your brain. So let's start with some vocabulary first. What does identity mean? You might have heard the term identity show up when solving equations back in the day. That an identity would occur, for instance, if I had this equation, if I had 2 parentheses, don't even write this down, I'm going to erase it in a second. 2 parentheses x plus 1 equals, let's say, 2x plus 2. And if I solve this, what do you think ends up happening? Well, I'd end up getting 2x plus 2 equals 2x plus 2. And I'd end up getting something that's true for whatever values of x I plug into it, where there was infinitely many solutions. And sometimes we said the answer was, it was an identity. Okay, where this side was equal to that side. Where there were infinitely many solutions, any value of x would work. Let's see, am I going to have enough? No, I don't have enough. So sad, so sad. Let's see. This is even worse. What am I doing, guys? Guys, what do I do? I forgot. Here we are. Here we go. How great is this video already? Like I said, the best part of the internet. So an identity is a statement of equality. Of equality between two expressions that is true for all ALL underline, super key word right there, all values of the variables. And I'll put the S for variables in parentheses, so it's got some like optional plurality there. And technically it says of the variables for which the expressions are defined. Whatever. All right, good enough. So an identity is a statement when anything I input for those variables will still result in that statement being true. So it's true all the time. All right, is the idea. Todo de los tiempos. So that's an identity. So a trigonometric identity, as you might suspect, is any time I have an identity that includes trigonometric functions or ratios in there. Okay, so we're going to be working with some trigonometric identities. Now, before we even get to an identity, all right, over the next 2 sections, we're going to be getting to the point of proving things are identities, and that's actually hard to do. Because to prove that something's an identity, I would have to literally prove it for all values of the variables, and I don't have infinitely many minutes of the day to do that. So we're not going to have an easy time proving them in that way. So we'd have to use some other techniques. But it's actually really easy to disprove an identity. And the way to disprove something is to use a counterexample. All right? Counterexample. All right, and a counterexample is a specific value of a variable that makes an equation false. Nope, makes an equation false. All right, and the interesting thing about counterexamples is that we actually only need one of them to disprove an entire identity. Okay? That's all that it takes. You don't have to have any more. All right? Because by proving it doesn't work one time, I've just proved that it doesn't work all of the time. Right? And that's all it would take. So let's start with a little example here. Let's prove that this is not a trigonometric identity by a counterexample. Prove that. Here we are. The following. Sine x times cos x equals tan x is not a trig identity. Okay, so if I want to prove that is not an identity, all I need is a single case where it's not true. All right, single case. So when doing so, I'd be interested in picking some values of angles, not necessarily absurd ones, but trying to find out what might break this down. So what's a value of x that you think I could plug into this that might break this? And maybe there's no intuition to that. Maybe we just need to start by plugging something in. Because it might be true some of the time, but it won't necessarily be true all of the time. So let's just plug in a value. What do you want to plug in for an angle? Give me some. 30 degrees. Let's try 30 degrees. And I'll even use 30 degrees instead of pi over 6 radians. So sine of 30 times cosine of 30, is that equal to tan of 30? Interesting. Sine of 30 is a half, right, using our hand trick. Cosine of 30 is root 3 over 2. And tan of 30 is 1 over the square root of 3 or root 3 over 3. Okay? And if I multiply these out, I can see that that's the square root of 3 over 4. And that is not equal to the square root of 3 over 3. So we have provided a counterexample. Therefore, that is not a trigonometric identity. All right? So even if the thing we first picked was true, we couldn't say, oh, it's true all the time. No, we've just found a single case for which it was true. Okay? That's the idea. All right. So that's the idea of a counterexample. The counterexample that I provided was 30 degrees here, technically, is what we selected. And my work is kind of what justified it. So let's do a discovery. We're going to discover some trigonometric identities based off of some things that perhaps we already know. So let's consider the following. Sine of theta, all right, facts I know. I know that sine of theta, 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 that's a Greek letter right there, just so you can understand through my slur of it or lisp of it, theta, right? Sine of theta is equal to y over 1, or plain old y, right? That's a true fact. We know that. We know that cosine of theta, or sorry, cosecant theta, my bad, is equal to 1 over y. Right? So if I could combine these two facts that I know into a third also true statement, I will have discovered a trigonometric identity. Now, what I want to point out here is, let's actually figure this out for sine. Suppose for cosecant theta, would it be true that I could reciprocate both sides of this and it would still be a true statement? Can I flip both sides of an equation? Is that a legal thing to do? Yeah, that's allowed. I can do that. So 1 over cosecant of theta is equal to y over 1. And wait a minute. Y over 1, I've seen that before. So by the transitive property, if A equals B and B equals C, therefore A must equal C. So check this out. So I just realized that sine of theta is equal to 1 over the cosecant of theta. Aha. And this is true for all values of theta, right? And oftentimes a lot of mathematics is pushed forward and discovered in this sort of way, where we merge together facts that are already proven true and discover new things that are also true. Okay? So this is a trigonometric identity. And this type of identity is called a reciprocal identity. I'm not going to discover all of them for us, but I'll give them all to us. Why not, shall we? So the reciprocal identities are the following. I know that sine of theta is equal to 1 over cosecant of theta. It turns out that cosine of theta, what do you think that would be the reciprocal of? 1 over secant of theta, yep. Because that, I mean, secant theta, we even called it earlier, the right reciprocal of a trig function. Tangent of theta is equal to 1 over cotangent of theta. And then similarly, kind of the flipperoo version of these. Cosecant theta is equal to 1 over sine. Secant theta is equal to 1 over cosine. And cotan theta is equal to 1 over tan. And all of these can be derived similarly to what we had just done moments ago. Yes. So these are called, as I said, the reciprocal identities. So these are true all of the time for every value of theta, and it would be good for us to know them. So we're going to incorporate some of these in today's problems that we do. But that's not all, folks. These are not the only identities we'll be learning today. Good news. Good news, everyone. Let's discover another one. And actually, this one, I believe we've already done before. Consider the following. I know that sine of theta is equal to y. I know that cosine of theta is equal to, what's that equal to? X. I know that tan of theta is equal to y over x. These are all facts that are true, right? We've known these. Therefore, and watch, actually, instead of writing the word therefore, mathematicians sometimes use cool little symbols. So if you draw like this little triangular point thing, sure, maybe the Illuminati. It just means therefore as a symbol. It's kind of like, you know, cell phone chat shorthand, LOL sort of thing. Mathematicians have been doing it for generations. It also kind of reminds me of the, doesn't Predator use some sort of laser pointing kill machine that has a little 3 red dot thing? Yeah, reminds me of that. So therefore, this is also true that tan of theta is equal to, and watch what I can do here. If sine theta is equal to y, I could plug this in here. And if cosine theta is equal to x, I could plug this in here. Right? So I'm kind of using the substitution property, something that's completely legal and allowed to do. All right? Tan theta is equal to sine theta over cosine theta. All right? And this is one of the quotient identities. Quotient. And there's only 2 of those, which is nice. Glad they kept the list short. Tan theta is equal to sine theta over cosine theta. And the other one is about cotan theta. What do you think cotan theta is going to be equal? How could you justify that? Anyone. Doesn't have to necessarily be Amber. Why do you think it's going to equal cos theta over sine theta? It's cotan is the reciprocal. I could technically have combined this fact that I just proved with this fact, right? And I could have combined those 2 in order to give me this fact with a little bit of work, not much. So, right, notice we could combine those previous truths into further truths as long as we're logically sound in our implementation. Okay, all right, good stuff, good stuff. Let's do another discovery here. And this is the last discovery we'll do today. There are more trig identities we'll do tomorrow. Here we are. Discover. Discover. Discovery. It sounds more adventurous. Here we are. Discovery. Fact that I know. Aha. Now, let me draw a little picture for this one. All right. When we had the unit circle, I'm pleased enough with that circle. And when I had a triangle drawn on that circle, this was x, this was y, the radius was 1, the point was x comma y, right? All sorts of good stuff. Now, what would the Pythagorean Theorem say about this triangle? X squared plus y squared equals 1. 1 squared, technically, or just 1, right? And this is true by the Pythagorean Theorem. Other fact I know is that sine of theta is equal to x, and cosine theta, nope, sine theta is equal to y. Ho-ho, settle down there, friends. Because, right, opposite over hypotenuse. Cosine theta is equal to x, because adjacent over hypotenuse. So combining these facts, what do you think I could say?
Sine squared plus cosine squared equals 1.
Yeah. Right, therefore, and actually, I like how you said sine squared, cosine squared, right? They end up switcherooing these as well at the same time because they think sine should go first. But yeah, and you also said it as sine squared plus cos squared equals 1, which is true. And what I want to point out about this is a little note that sine squared theta means sine of theta all squared, okay? This is a shorthand way of writing that. I don't believe you guys have seen that before this point, all right? And I guess similarly, these are not equal to sine of theta squared. Question, comment?
Is it 1 or 1 squared?
Well, they're mathematically equivalent, so we just drop the square just to simplify it. So I just want to point out that sine squared theta, that's literally how you say it. Sine squared theta means sine of theta all squared. Mathematicians will be using that phrase so frequently that we figured, hey, let's use some cool shorthand, right? Why not? Why not? So this, justly named, is called one of the Pythagorean identities. Right, and isn't this kind of cool, like just being able to use any math fact that we know is true and just like mashing them together into like new math facts, like, and that's the nice thing about math is the things that we discover that are true and we know are always true will always be true forever, and we can just like apply them and combine them and synthesize them into new concepts. So let's see, Pythagorean identities. We've got sine squared theta plus cos squared theta equals 1 is the first of the Pythagorean identities. There's 2 more. We're going to discover one of them, and the other ones will maybe explain how to discover it. But I'll write them all down now for you. The other one is tan squared theta plus 1 is equal to secant squared theta. Huh. Interesting, interesting. And the last one is that 1 plus cotan squared theta is equal to cosecant squared theta. Good stuff. And just so, I don't know if you're interested, the way I memorized this last one is that the C and the C kind of go together. I don't know. But yeah, you should familiarize yourself with these, have them memorized, because I'm certain that your calculus teacher would want you to have these memorized. Yes, that's true. It's true. So let's try a little thing. We haven't done, well, I guess we've done some discoveries, but what if I was trying to actually intentionally prove that tan squared theta plus 1 is equal to secant squared theta? Using any of the previously proven facts that we've had. How do you think I could go about proving that? Well, it turns out it's related to the other Pythagorean theorem, Pythagorean identity, the one that we just found. So let's start with that. So if I'm trying to prove that, let's start with, okay, if sine squared theta plus cos squared theta is equal to 1, how could I go from sine squared to tan squared? Yeah. If I divide this by cos squared, and if I divide that by cos squared, I have to divide everything else by cos squared. All right. Now, what trig identity would allow me to rewrite sine squared theta, cos squared theta? What would allow me to write that as tan squared theta? That was a, no. It was one of the, which identities? Quotient identity said that tan of theta was equal to sine theta over cosine theta. Squaring it does pretty much the same thing. Okay, what's cos squared over cos squared? Plain old 1. And what is 1 over cos theta equal to? Secant theta, so it's the same thing with squares. What trig identity allows me to make that adjustment? That one's a reciprocal identity. Right, so that's a recip identity. This one was a quotient identity. And this one we started with a Pythag identity. All right, we're going to actually, in the next section, we'll end up doing some verifying trig identities and kind of experiencing a little bit more of the proof side of things. But I just want to point out, get you kind of used to the habit of it. None of your homework problems tonight will require you to prove them. You will, however, be required to disprove them. And how do we disprove them? With a counterexample, right? A single point, a single case in which it fails or breaks down. So let's do a couple of examples putting these to work for us. All right. All right. Here we are. If secant of theta is equal to 3 over 2, then find cosine of theta. Okay. So now, if I'm doing this problem, there are other techniques we could do, drawing pictures and stuff of triangles and figuring it out. But let's strictly use some of the identities I have. What identity do I have that relates secant to cosine? That's one of the reciprocal identities. Which reciprocal identity would be helpful? Well, I'm looking for cosine, so let's do the one that's in terms of cosine. I know that what? Cosine theta is equal to what?
1 over secant.
1 over secant theta. So using this identity, all right, one of the recip ones, right? I could say that cosine of theta is equal to 1 over 3/2. So cosine of theta is equal to 2/3. All right. So 2/3 would end up being the answer. So I was able to use one of my identities. I just found out, okay, which one is going to bring me to the other, which identity is actually helpful in this situation. And that works okay. Now, I mean, technically, we could have, tried to find a way to secant inverse both sides, which is essentially still going to have to use cosine inverse and do all sorts of work. But let's just use the plain old identities and figure that out. So this is the easier type of situation where you look at your trig functions that you're relating, and you try to find the link in as few steps as possible using your trig identities. So you guys picked the right one. You found one that relates cosine and secant. However, sometimes they can't be done all in a single step. All right. So let's see. If cosecant of theta is equal to 4/3, find tan of theta. Okay. So looking through our identities, right? I mean, I've got this one. I'm trying to relate cosecant to tangent. I've got cosecant to cotangent. That's not a connection. What could we do? Let's see. Any of the other identities helping us? Right? No, none of these have cosecant. There's a tangent, but that's not necessarily helpful. What do you guys think? Here's a cosecant one to sine. Go from sine to tangent?
Don't you need don't you just find sine and there's quotient identity?
Well, but the quotient identity, once I know sine, I'd still actually need to know cosine. I'd still be short one. So I could get to sine, but then I'd still have to find cosine, which you could do. That would be a 3-step, right? Oh, oops. I just like tore space open there. So check this out for this problem. Here we are. There's 2 ways we could do this. We could use a Pythag. All right. What Pythag relates cosecant? I have 1 plus cotan squared theta is equal to cosecant squared theta. I could use a Pythag and then combine that with, once I know cotan, I could find tangent using a reciprocal identity, right? Where tangent theta is equal to 1 over cotan theta. So this would be like a 1-2 step, all right? So I view that as like 2 degrees of separation, all right? So let's do that one for starters. So let's see. I know cosecant is 4/3. So 1 plus cotan squared theta is equal to 4/3 all squared is what that means. Because remember, the square here is applying to the whole function. If cosecant theta is 4/3, it's 4/3 all squared. So let's see. So what's this simplify to be? 1 plus cotan squared theta is equal to, that's 16/9. Now what could I do to both sides? No, I'm trying to get cotan theta by itself. So I'll subtract 1, which is the same as 9/9. So cotan squared theta is equal to 16 minus 9, 7/9. And I still haven't solved for cotan. I've got cotan squared. What could I do to both sides? To get, yeah, root both sides. And technically that would have a plus or minus showing up here. So I'd get cotan theta is equal to 7/9. Or no, sorry, root 7 over the square root of 9, which is 3. So plus or minus, right? So now let's find tangent, right? Let's see, I know this one. If I now plug this value in here, I can find tangent. Right, that's not that bad. So that means tan theta is equal to 1 over this value. Right? So that's equal to plus or minus 3 over the square root of 7 if I just reciprocate. And how do I get the root 7 out of the denominator? Multiply by rad 7 over rad 7. And we will get tan theta is equal to plus or minus 3 square roots of 7 all over 7. And we could get decimal approximations for that if that's what we were looking for. All right, so this was like a 2 degrees of separation problem. All right, and those are a little bit harder because I realized, okay, with cosecant, I can get cotan. From cotan, I can get to tangent. And technically, there was even another option that I thought of, which was 3 degrees of separation. you could have gone from a reciprocal function, right? So I could have found sine theta is equal to 1 over cosecant. You don't have to write this down. And then from that, so I could have gotten sine. And then from sine, I could have gotten cosine using this. Right, which is what someone was kind of describing going for sine first. And then once I have sine and cosine, I could then use the quotient identity tan theta is equal to sine over cos. So that would be like a 3 degrees of separation sort of thing. And that still would have led me to the same answer, but it would have just been a little bit more work. So the skill that you're going to have to use is trying to find ways to relate these one to another. And actually, the degrees of separation, I don't know if you guys have ever heard of the game, the 6 degrees of separation. Usually it's related to the actor Kevin Bacon, where you will name someone like Christopher Walken, and then like the object of your opponent or whatever is to try to connect as many movies or things that like, okay, Kevin Bacon was in a movie with this person who then wrote and directed this, which then this person played in, which was also in a movie with Christopher Walken. That's like 4 degrees of separation. I don't know. It's a weird thing people do. But it reminds me of this because we're trying to find connections between, right, cosecant and tangent. That's what it reminds me of. So anyways, friends, thanks. Have a great day. Bye-bye.